All right. So here we are in week 4 of foundations, and this is our second week of metal shop, where we're going to talk about sort of the processes of the metal shop. And as always, please feel free to hop in. There will definitely be situations and cases where you know more about these things than we do, and we'd love to hear from you. If we say it wrong, if there's more to know, if you've got all sorts of things to add in, please feel free at any time to just revise our thoughts and ideas so that we can be as helpful as possible with what's going on. So we're going to talk mostly this week all about, let me put my cursor on the right thing. We're going to talk about soldering, brazing, and welding, sort of putting those three things together because they're related processes that feel really, really close, but they're not exactly the same. And there's some nuance to them that we can go over. We'll talk a little bit about jewelry making and some processes. There's a lot of videos that are linked in these slides that are worth watching. So if you have, if you've been thinking about stuff to do, there's a few videos in here that are kind of our favorites in a lot of ways if you want to nerd out on things. Some basics about tempering, and then the lathe and milling basics, CNC overview, sort of conceptual. This isn't so probably you won't be doing CNC things this week, but it gives you a sense of like where that is going and how it's sort of a spiritual successor to a machine like the Bridgeport. And then the water jet cutting, which is just a lot of fun. How many of us have gotten the water jet badge? Yeah, that's a bunch. It's a fun tool. And then electroplating. So we'll talk about that, which is good chemistry. So we're going to go through these things to try and make sense of as much of it as we can. And so we've got soldering, brazing, and welding. So first up, soldering is the smallest of these processes and the lowest temperature. And there's a whole paragraph. Don't read it. This is actually bad slide form. Just read the white part. Items are joined together by melting and putting together a filler metal, which is the solder, spelled like soldier solder. It's a weird word. Putting that melted metal into a joint, a connection between two base metals that do not themselves melt at all. So when you're soldering, you're putting a metal glue between two pieces of metal that don't change. That's what soldering is. It can happen for a lot of different purposes, a lot of different things. You might solder pipes. You might have heard people talk about soldering or sweating a pipe together. We'll see that that's sort of like in the borderlands, maybe almost for some pipes. A lot of it that we're going to talk about is sort of soldering for jewelry. So this is perhaps the most relevant type of soldering for what we'd be up to this week, is soldering jewelry like you might see here. If you've got some bands, these are fire bricks, a little tiny torch, and then some soldering rod. You can also solder together chain links and other different things. But soldering also applies to electronics up here. And so spiritually, these are all really similar in that you have a base material that you don't want to have melt at all. And then you put molten metal in between to make some sort of a connection. My brain, that is coming from my physics background, is thinking about soldering like this every single time, just because of electronics. And in that case, you really don't want your base material to melt because it's like a transistor that you need to have operational. And so you don't want your base things to melt at all. Whereas in jewelry, sometimes it can be okay for the pieces to be a little melty, like they won't break if they melt a little. But usually they're very precious metals and you don't want them to discolor, or there's some reason why you want them to stay exactly as they are. So soldering is a great purpose for that. This is the coolest of the processes that we're going to look at as in actual temperature. The soldering irons for electronics downstairs, I was just looking at them. They're only 700 degrees Fahrenheit, which is hot. And I've done, it's enough. You will get a burn if you touch a hot soldering iron. Or fumble it. I have been in a school teaching kids to solder and like reflectively grabbed the fumbled ones. It comes, your skin grows back. It's fine. But the other processes are much hotter, and so they're likely to be more of a threat. Soldering is a great place to get started if you want to do that. Soldering a pipe in your house, a copper pipe like this, is pretty approachable. And electronics, we're going to play around with some as we move forward. The real like magic trick for me, coming from an electronic soldering perspective, is soldering jewelry is often a complicated multi-stage process. So this is something that's worth looking at. We found this on Etsy. And so all props to Liz Door Jewelry for putting their photos out public on the internet. but this is a lovely piece of jewelry they've got. And over here, these are where we expect their solder lines would be. This is sort of trapping in this lovely stone. They did a nice job here. And so they've got these red pieces that we're assuming, I talked this over with Lisa, who's the metal shop facilitator. She thinks that they may have used a hard solder here, which would be something you do first. It takes a little bit more temperature to get a hard solder to melt. If this is made out of gold, the gold that's there, you wouldn't want to have melt at all. The hard solder would melt below the melting point of gold. So it would connect those dots, it would make the little box, and everything would be nice and solid from that. But then if you've gone to all the work of soldering up a box and trapping that stone in it, a jewelry soldering job might be the next round happens with a medium grade solder. And medium melts at a lower temperature point, so you don't risk melting the solder joints that you just made in the previous round. So if you're going to be hopping into the jewelry area, and we know there's some barriers to hopping into the jewelry area, and that's a tricky thing. It is possible to do multi-stage soldering with this sort of a system where there's hard, medium, there's actually a soft solder as well. But a lot of the time, people can get along with some of these. If your piece is really big, you might be able to use the same kind of solder. But if you have something that's really small, it's possible to make complicated solder connections with multiple stages of doing this. In addition to that, and this is new, I didn't add a slide, but another new thing that we should say, we just got a badge for the IACast casting machine in the metal shop. That badge just happened like 2 days ago. Lior just made it happen. So if you're interested in metal casting, that is totally a thing. And downstairs, there's a copper MakeHaven robot that it's full solid copper that looks like a 3D print, because it was a 3D printed thing that we then made into a full copper cast. So it's really cool. The detail's incredible. Julia, you saw it?
Oh yeah, it's super cool.
It's really neat. Well,
Burn out the PLA.
yeah, they burn out the PL. They did it. They did the.
It's metal castings.
Yeah. So it was the 3D print into plaster. Then they burned the PLA out of the plaster, and then they did the kayak cast in there. And I guarantee.
Not used in, but I guarantee.
Yeah, I guarantee it's the example Lior used in the video, which is probably going to go posted in a week or so,
Yeah.
whenever he edits it together.
I'm still badgered for kayak house.
That's a great question. I don't know. Yeah.
Find out together.
I was I made a little message channel for a few people who had expressed interest, and Lior said, like, then 2 days later, oh, I just started making the video for it right now. Part came in. So if you want to make metal castings, it is now possible. It's really cool. And it's a copper part, so he did it with molten copper, which is really cool. So let's say your jewelry is neat. This happens at sort of the lowest temperatures you're going to get involved in these processes. And then brazing is sort of one step up. Again, ignore everything but the white text here. Metal items are joined together by melting and flowing a filler metal, so really similar. And the filler metal is still going to have a lower melting point, but usually there's like a flux and you're getting really close to the melting point of the base metal. So the base metal may melt a little bit, the like part that you want to have joined may melt a little bit, but you're really, really close. And so this is something that you can consider. So copper, this is sort of like on the border a bit for melting points, but brazing is often like an aluminum tubing thing can happen, where you have aluminum can be brazed pretty easily in a garage at home with a torch. Aluminum has a lower melting point overall, so like you can get aluminum brazing sticks pretty commonly at a Home Depot or Lowe's, and then you can get things to go together. Brazing is also really easily done on a conveyor belt, so it's not an uncommon manufacturing process where you can have a filler metal sort of flow between two pieces here, as opposed to like big robotic welders that have to be a giant robot arm that lays a weld. You can do this with just like pass it through a real hot oven where it is controlled for temperature just below melting the base metal and just above the brazing metal. And you can get some really neat things. Like this is just a big crack in a piece of metal that has been brazed shut. If you have a giant iconic American bell, you can braze those cracks shut as well. So there's lots of different ways that you can take cracks and fill them, or that you can make bonds between things. Brazing is sort of an in-between land. between soldering and the next one, which is welding. And so welding is the one that like is the highest heat. It melts parts together, allows them to cool and fuse, sometimes with a filler metal and sometimes not, but it always requires melting of the base material. So when you're welding things, if you weld two pieces of steel together, not only are you maybe going to have some filler if you use the MIG, you're going to also melt the steel that's there as well. So all of those are true. And if you do oxyacetylene or forge weld things, you may actually make a weld without needing any filler material, and they're just so hot that they fuse together. You were trying to forge weld just a bit ago. Yeah?
Should have brought my first attempt,
It's probably still pretty toasty, I would guess.
later. I quenched it.
All right, well, there you go.
I accidentally melted steel earlier, which isn't something I've ever been able to say before.
Welding, however, has this whole host of things. Welding often looks like this, although you can't look directly at it. It's really a lot of light, more than your eyes can handle. So you wear a mask like this. Welding is something that's widespread across production of various types. It's how you get pieces like this or like that. Lots of sparks fly. It's really fun. You feel like you're Norse god in lots of ways, putting things together. It does happen underwater sometimes if you're building a bridge. I had a kid 4 years ago, very vividly. He knew he wanted to be an underwater welder. Like
Super dangerous.
it's really, but it like I think it pays about the same as a doctor job pays. So like, yeah.
Videos of crabs getting stuck by like the gravity or whatever.
Yeah.
It's crazy.
It's nuts.
Dead in an instant.
Right. It's really like, and it's done by electricity. So like you're in the water with a bunch of like, you got to know what you're doing. Is the short version.
So did he become it?
I would need to follow up with the kid. You don't always get to find out. And I hope he did. But no. It's one of those things.
It doesn't pay as much as it should.
It does. Oh, really? Oh, yeah. Wow. No,
It's
that's
like a range, but
What's the range?
the range is 10,000 to 203 per job.
yeah, that must be 10,000 a job.
Salaries of underwater
How
welders
to seize your $300,000 your underwater welding salary.
with a mean salary of 37,000.
Oh, that's rough. Okay. All right. Well,
One else like you're.
okay. In any case,
Taking my own edits.
above water welding, above water welding is what we'll be doing. So that's yeah. No, don't do it. All right. So welding, we're gonna stick to this, but it's really fun. There's all the equipment downstairs. You don't need to have your own if you're looking for another badge to get and you're just like still at a pause. The MIG welding badge is a ton of fun and it's a good time. Please.
Is there like a start with a MIG and you graduate upwards, or can you go that straight to take welding? Is it like better to?
MIG is by far the easiest because you just like press the button and it happens.
The hot glue gun.
Yeah,
I
yeah.
just don't think well, and it's not.
So you're asking good questions. So there's
Saying unfortunately, I think is what I would have to get for bronze.
no, there's a whole range of different types of welding. And so there's MIG, where it comes out of the gun, it's a hot glue gun. Then TIG, where there's a TIG cup where you hold a thing that makes an electrical arc to what you're trying to weld. And then at the same time, in another hand, you're pushing in the filler material. So for TIG welding like that, you have things to do in both hands. So it's a little more complicated.
Pedal the control.
And a foot pedal often. Yep. Although I think ours has a finger button. So like you have 2 hands and a button to manage all at once. So that's step up. And then there's oxyacetylene, which is just like oxygen and acetylene. So 2000 degrees of fire that you point right at the thing. You may want to put a filler in, but that's hot enough for most metals that like you can just melt them until they're melted together. And that works fine. It's also a good way to cut through the metal if you just want to like sort of melt them enough that you can make a cut.
God for detail on this tonight.
Yeah, no, it's that one's those. I think it's one of those that sort of like there are people who will only do hand woodworking. There will people who will like, if you can't oxyacetylene, what are you doing? Right. So it falls into that same sort of camp. But I would say if you've never tried it, trying MIG is good. A TIG welding job is going to take more kit, but it does give you more options. And then there's stick welding, which I don't think we do a lot of here.
I think we're set up to do it, but
Yeah,
there's not a lot of reason to stick
when you have the other options.
yeah.
Stick welding is like what you do in your garage when you only want to pay the least amount of money to make a weld, which is totally reasonable and like completely a thing I would do in a future garage that I might have. But MIG welding is the easiest if you've got the equipment for it. So I would recommend. And so if you're trying to compare these, this is a lot. Don't stare. We're not going to try and explore all this now. But soldering is got all of these different things. Is the bond structural? Soldering is more for like delicate structural bonds, like jewelry is great, electronics are great, but like you probably don't want to make a bike with a bunch of solder welds. You may braze together a bike. That's fairly strong, and welds are the strong. You build bridges with welds. So like there's basically that's the key difference between the three, in addition to temperatures and heats and like what's the materials. So there's some subtlety, but the simplest way to think about it is soldering and brazing. There's a fair amount of overlap, but those are sort of lower temperature and they both require a filler. Welding is hotter and more, it's the only one that melts the base material. So it is sort of separate from the other two. So jewelry making. Jewelry making is a really cool process that you can come after in lots of different ways. Every piece of jewelry that's shown here is a metal piece of jewelry because we're in the metal weeks. But lots and lots of types of jewelry are not completely and entirely metal. These are just fun examples to get you inspired. Some of these, though, come through with really cool ways. Like here's a really large chain link that's a lot of fun. These are sort of shaped copper flower petals that are really neat. These elephants are really adorable and could be cut with a handsaw, like a delicate little handsaw. You can cut those elephants. Same deal for these. You drill a hole and then you just by hand cut a little plate of copper into this shape. You get some really cool looking jewelry with a surprising amount of detail, doing it by hand with delicate timing, and then very carefully sanding and putting things together. These look like they're soldered together to me, these three layers. I think this would be a great example of this copper piece was soldered on with a hard solder, and then the one that's on top of it was put together with a medium. So sort of going through the steps, or maybe in the reverse order. Maybe they put the small one on this one first, and then they went on to the big one, and then just cut the big one out. So it's easy. Only need to align it once, really, and then use the biggest one to shape afterwards. But making a chain is another thing that you can actually do. So it's something that it takes some skill, but I've watched Lisa, the facilitator, just like manifest a chain right there in front of me. She just took a copper string, wrapped it around a stick, and then started making cuts so that they turned from a sort of a copper spring into a bunch of jump rings that she's able to just sort of magically twist together, and it turns into a chain. And so I'm going to play this and mute the audio, but this lady talks you through the process of taking some copper wire, making a spring like this, and then doing exactly that. So she's going to take this thing and moves it off of a metal device, puts it onto where would you come on over here. Yeah, so she can saw that way through this particular thing, and she's able to cut that spring on one side and be able to get jump rings that can go together. Sometimes there's a lot of different ways that you could do this, but it's really possible to do this even with like a stick of wood. You can do this without needing the jewelry shop here at all. But it's really nice to be able to use some of those tools, even if you grab sort of a saw and come out from there. Oh, and this is the process I saw Lisa do. You just take a coil, push it near the end of a dowel, and then you sort of cut at an angle. So you're really just cutting the 1/2, and that gives you your split ring. So if you wanted to make chains like this, it's pretty approachable to do. It's a very you can make it happen sort of thing. And a big chunky chain can be a lot of fun. So this is one of 4 videos that cover these processes. You can do all different kinds of chain lengths. You can do sort of these fancy loop and loop chains, or you can do wrapped wire techniques, which can be a really fun thing to pound into a wood piece. Also, if you have a little wood, if you made like a little jewelry chest and you made a little groove around the top, you could make a twisted wire like this and sort of pound it into that groove, maybe a little epoxy so it stays. And it can be a really nice way to add some detail to a wood piece that you've made. Just a really neat trick also. This is as easy as take take a wire, you put it in a drill and it spins it, which makes it straighter, which is kind of bizarre. And then you take two and put them in the drill and then you spin those and they twist usually in a really nice progression. Although they found a way to make a like 8-minute video about it. It's, you know, YouTube content. But in any case, making jewelry like that is really fun and approachable. So I would recommend those if you're interested. Tempering is a cool process. And in Slack and the Foundations channel, I shared, you know, my video feed on YouTube when I like get home and sit down on the couch for 10 minutes before getting up to make dinner is usually like some weird making process. And so today, it was this old Tony's You'll Shoot Your Eye Out Kid video where he goes through the tempering process, showing how you temper different music wire, different materials. So if you want to see tempering and annealing, it's a really fun way to see it. But basically, heating and cooling metals, especially iron-based metals, can change their properties a lot. The tempering colors that you can see here, they tell you what temperature your metal reached. And if you look at something like this sword, you can see really nicely how hot the sword has gotten and sort of where the color is and what's going on with these different things. Tempering like this can be very useful. It'll also show you, if you get the welding badge, you'll see this pop up on the pieces of metal that you weld. And the bluer it is, the hotter it has been. And the like straw color happens when you hit about 400 degrees. And so you've got this range that can let you do different things. If you have a piece of metal that you want to make harder, a piece of iron that you want to make harder, you totally can. And the basic process is heat it up real hot and then quench it in water or oil so that it cools off really, really fast. That'll make it very hard, but also very brittle. And then if you want to make it tougher by letting it be able to bend instead of snap, you'll want to raise its temperature and let it stay there for a long time. So if you want something to be bendy, you want to put it into an oven where it can stay 500 degrees for 2 hours. And that will make it softer and more bendable.
Is it the same as working with like jewelry silver where you can dip it in acid and turn it back to its form and redeep to the color you want?
That is, yes, if you're talking about just the surface finish.
Yeah, heating the metal,
Yeah.
different metals. Is that the case for?
No, I'm gonna Google it on this screen in case I got the vocab word totally wrong. In copper, they call that fire scale. And fire scale copper. I think it is fire scale copper. Yeah, if we look at this fire scale and copper, yeah, some people really love this look. Lisa actually really likes this look on her jewelry. This is something that can happen, and people will deliberately do it to copper where it changes colors and a little bit of acid, and this is like a surface detail on copper. And so you might cover it with a clear coat to keep it on there so it doesn't rub off, if this is the thing you want your jewelry to look like. And so you can make this happen a whole range of ways. I think it takes a fair amount of work to make it look that fun and splotchy.
So if you weren't working with jewelry and you're just working with pieces of metal,
yeah,
you can still formally change its color.
Yes, these are, the colors that are here, these are for steel.
Steel. Okay,
And
I guess that's my question.
Yep, and they're like at the surface. So if you have that on your surface and you sand it down, it'll go back to just steel color.
Okay, yeah.
Yep, in the same way that the copper jewelry would. So that totally works the same. In the case you're talking about, they probably use acid because they don't want to remove anything that they don't have to. So instead of sanding, you use an acid to take off the top layer.
Yeah.
And so this totally works to do that. In a knife for like the kitchen, they will totally have removed this color so that when they sell it, it just looks like a plain piece of metal. But they probably hardened it and then they probably did the hardening process where they heated it and quenched it, which would make it very hard, especially on the edge. And then they probably tempered, if they could, they'd probably temper just the back half of the knife where it's thicker, so that the front edge where you cut stays really sharp and really hard. And the back side of the knife is a little more flexible and a little bit more pliable. Katana tempering. These are Yeah, this is really like, if you really want to nerd out, making katanas is an incredible thing. These swords have that curve in it because of the dynamic of tempering and quenching the sword itself. So there's like it's got a bow in it because of the dynamics they put into the metal. So they stay sharp very, very long, but are able to be very light because the cutting edge and the back half of that blade have very different metal properties, which is bonkers. It's I don't have you seen anybody make a katana? It's like it's a big project. It's like I mean, you could make something that looks like a katana, but to make one that's got the proper like tempering and everything would be a monstrous undertaking. Yeah. Like in the case of these beautiful hand carvings, that's really cool. The impressive part is still the sword, like with all the crazy metallurgy that goes into it, and that's very impressive. I don't mean to decry that.
So how does tempering increase toughness?
It has to do with the internal grain size of the metal, and when you temper, the grains can get a little bit bigger, so they can sort of slide past each other and bend a bit more. Your toughness and being brittle, there's a lot of really heavy vocab in there. So like being tough means it won't break, and brittle means it will break, but you can be very, very strong and you're very hard, but very brittle. So like you won't dull the knife until it shatters, right? If it's very hard, but if it's tough, it's probably not the sharpest thing in the world, but it won't ever snap on you, right? It's an interesting dynamic in metals, but probably most of us won't be too deep in those weeds. But it's good to know, good to look at. And if you happen to be doing something where you make metal chips like this, you can get real fun colors and you can tell the temperature that they were at as a result. Yeah. So there's a bunch of reasons why metals have colors. And so this is just, I want to say these out loud more than anything. The first one, if you get a metal glowing hot, that's something called black body radiation. It's a fascinating science phenomenon where like when things get so hot, they'll just start glowing. And it turns out, in case you wanted to know, the sun is an example. The sun is not on fire. It's a big glowing hot ball of gas, in case you wanted an astronomy lesson to go along with it. In order to be a fireball, it would need to have oxygen so that it was burning. Instead, it's just glowing hot hydrogen and helium. And so it's glowing white hot, which is its own whole crazy story. But in the metal shop, you probably won't see it until you weld something. And then when you finish the weld and pull the goggles up just a little too early, it'll still be sort of glowing orange, red. And as it cools off, it'll stop glowing. So metals can glow when they get really hot. You were using the induction forge.
Does some forging. There's a shield that you want to wear that's I think tint 3. There's tints to perfect your eyes of various grades. So welding will be like tint 12. And this is just 3 to take the edge off because it gets so bright. And before I put the shield on earlier today, I was getting, the spot in my vision, like if you glance up at the sun.
Yeah.
Which can be bad for your eyes over time.
Yep. So that's an interesting thing. More interesting is rusting and patina. We probably interact with this a whole lot more. Rusted metals, everybody's commonly aware of a rusted metal. It's got this reddish brown color, and copper will also rust, but it's called a patina usually. It's often a preferable thing for copper. Turns this blue color. The Statue of Liberty is made from copper, and so would have started off orange and then over time turned this green-blue color, which is an incredible amount of copper that France gifted to America. Like unbelievable, oh my God, amount of copper. But copper that you get is, one, it's going to be expensive, and two, it is going to be stay that orange color. The fastest way I know of to make it turn blue is to pee on it. Actually, it's sort of weird, but it works. Something about the chemistry in it. I've had multiple artists tell me that that's the way they turn their copper blue, which is fascinating. Yeah, I think you can also just like paint it with a thing. It was a bunch of dudes. I don't know. That was probably. I didn't ask follow-up questions. Yeah.
The other thing about rusting versus patina, steel and iron, incredible materials with the gazillion amazing properties, except steel rusts, and rust is actually continuing to eat away. I last week got to replace the catback exhaust on my 2005 Subaru Outback because part of it had completely rusted in half. So rust just keeps on going, eating away versus the copper patina or a lot of other metals form oxide layers like that, where it actually protects the metal underneath from getting eaten away by reacting with its environment.
Yep.
Steel doesn't do that,
Right, yeah.
unless it's stainless. Stainless is
And then it's the chromium in it that does it.
Yeah.
Aluminum is a good example. Aluminum does not rust. It'll pit a little. That's a weird thing. Aluminum, every time you've seen aluminum, it actually has an oxide layer on its surface. As soon as the knife separates from cutting the aluminum, it instantly oxidizes just from the 20% oxygen in the atmosphere. And so every time you've seen aluminum, it's always got an oxide layer on it. But it, like the patina for copper, it protects it so that it will not further corrode, which is great. And mill scale is a thing that if you're getting hot rolled steel, and you might know if you're getting into that, it's sort of got this bluish appearance on it. Or if you put it into a forge and get it hot, it'll sort of form on the surface. If steel gets really hot, you get these blue sort of solid, multiple layers, thick oxide layer. And a blacksmith is where you'll see a lot of this. If you go look at our anvil in the metal shop, there's some mill scale near it, but it protects the surface. And a lot of times, like the steel mills that I used to live near in Cleveland, that you would see the metal with mill scale on it because it does prevent rusting until you knock it off, and then it just starts to rust like mad, actually. But it's a really good way to work. You don't want to weld through it, though. It's not good for that. But if you start working with the anvil and the forge, you're going to totally notice mill scale. And that's just a part of how it works. But it's a light blue color. So, lathe and milling basics. Taking a look at these things. These are two, if you want to nerd out on the history of machining, these are two videos that are worth watching. I also find this particular YouTuber has a pleasant voice to listen to. It's just one of those like, good, I'm going to watch this and fall asleep kind of videos. But this in 1751 is when the first lathe got turned on, the first like machine lathe. There's older than that lathes by a landslide coming from various cultures from around the world. But the first machine lathe that's well recorded in history was 1751 in France. And so this is where things like the screw got defined. They did exist before, but shortly thereafter, they were defined in ways that became pretty standardized pretty quickly, and they let us have more precision in what we build. So instead of like, I mean, we're in New England, you can see lots of old wonky houses that were built in all sorts of ways that definitely look crooked and bent and strange, which is a lot of fun. And so those were built, but not with as much precision as something like the lathe would have come on. Construction now has much more precision baked into it. So a house built in the 80s or the 90s won't be nearly as whopper-jaw as one built in the 1700s. Right? That's an expression of the amount of precision we've had in our tools and how well we can build things to a higher quality now. Arguably, depending on what you value for quality. But these metal lathes in 1751, they really are what turned on the ability for the Industrial Revolution, which is kind of fascinating to think about. That's enabled by the machines that we have in our basement. The metal lathe looks like this. This is a big one. There's a whole bunch of controls and a whole lot of things going on. This is, I think, from the manual for our big lathe. Maybe no, this is our big lathe down here, and this is the smaller one. You can use them for lots of purposes. You can use them to put threads on things. You can use them to make different size spindles. But basically, the lathe is all about spinning materials. And so using this tool is a lot of fun, and you can make a whole lot of things with it. But there is a very long class for it. But if you're interested, it's totally worth doing. It's very much the spiritual cousin of the wood shop lathe, but everything on the metal shop lathe is not done by hand. With the possible exception of some sanding and filing, maybe if you want to. But most things on the lathe, you take the tool that you're going to use, and this is mounted. This is the tool holder up here, item number 2. This is where you'll swap in the different tools. So instead of holding them on your hip like you would for the wood lathe, you just mount them in there. And then with the big knobs and dials on the front with some of these, you can move this thing around and it'll make the cuts for you because the forces on it are so extreme. You do not want to be holding the thing in case something goes wrong. So the metal lathe is a really useful tool if you want to make stuff. Taking that and sort of spinning it up on its end is the Bridgeport. The Bridgeport machine, here's one of our two that we have. They, instead of spinning the workpiece, they spin the cutter. And so the cutting tool is a spinning piece. So there's a whole range of what those cutters might be or look like. End mills are commonly it. So they look like the spiral thing here. And you can see this is just slicing right through a piece of metal. And so a Bridgeport will cut through a piece of metal with no problem whatsoever. Other than that, they look like a large drill press because kind of are. They just need to have much more rigidity and stability and precision to do the jobs they're commonly asked to do. So they're another very large class that you need to take with a certified instructor because they do have the potential to throw a lot of energy into a thing, which means that they have the ability to be dangerous, but they are really useful. One thing about them though, if you're running a machine shop, is you can make a whole lot of stuff. And like, here's an end mill sharpener. If you get really into it and you want to keep making things and your end mills get dull, you can sharpen them back up again. But this is useful to look at just to sort of see. I'm just going to show this muted. So this is the same video twice. I would really recommend this one. We'll do this full screen. Here's sort of the Bridgeport doing its thing. You can see it looks a lot like a drill press. There's this quill. You move up and down. Here's the cutter. And as you go through, a few knobs will move things around. So instead of the drill press where you have to manually put the piece of wood where you want and then you drill, the milling machine or the Bridgeport will let you manually move it around with knobs and wheels so that you can control. And up here, this thing that's not turned on for him is a digital readout. So you can see exactly, and it's measuring as you do it. Where is it located? How's it positioned? And if you get really good at using one of these DROs, you can be very precise with one of these machines. So prior to the CNC revolution, which happened somewhere in the 50s is when they started turning up, people just got very good at building these things. So in World War II, this is how metal parts were made. Most often, people just learned how to do this, and they would be able to crank things out of these sorts of machines, building all sorts of stuff. And yeah, they're Bridgeport, like Bridgeport, Connecticut, where they were made, which is kind of fun. And so there's all sorts of different ways that you can do it. You can see here, here's the DRO. It's able to read with great precision based on the movements that you make here on the inputs. So you can make really accurate motions with these. It's definitely a skill to learn over time. It's not something you can hop in and know how to program. You got to learn some of the details of how to do it. And here, but you can see it's just slicing through that piece of metal. So that end mill is able to make cuts and do things and get really good detailed cuts through pieces of metal that other machines would struggle to be able to do. But it's kind of fun to watch. I would doubt it, I think, but maybe. Are you going to Google it? Oh, thank you. This is just where they're manufactured, like Toledo, Ohio, close to where I grew up. They're famous for scales. I think they just made good ones. Like, yeah, they didn't invent the scale. But it might. There's different, like every country I think has their own like famous brands of them. Like I think a Maho is a Swiss made one, maybe. There's different brands from different countries, and they're very proud of those heritages. The CNC is sort of the spiritual successor. So you'll see this in this video, or this half of the video, where a lot of what is going on, it feels the same. There's a vise, there's a table that moves around. So he's going to point at things for a while. And it's doing basically the same job. The difference here is that this is controlled by a computer. And so instead of you needing to be good at turning those dials, like look at how fast it made that turn without a pause, right? This is now controlled by a machine, and you can get very precise things. Like this is doing a little spiral down into the metal. That would be just about impossible to do on a Bridgeport. You'd have to be moving things with 3 hands at once to do a downward helical spiral.
Fun fact.
Yeah.
The milling machine was created by Eli Whitney in New Haven.
Whoa.
And then the Bridgeport, specifically, the Bridgeport Metal Goods Manufacturing Company was organized in Bridgeport in 1909 by a Danish immigrant. Just saying how much I love the Danes.
Yeah,
So in what situations you wanted regular hand Bridgeporting versus decar or the CNC?
Basically, this nowadays is always gonna be, there's a lot of stuff you can only do on CNC, so like Corey was saying, doing a downward helix into a piece, you really can't move two axes at the same time with any precision on a Bridgeport. So making cool shapes with curves is really something you can only do with the CNC. That being said, I think a lot of machine shops still will have a manual Bridgeport and a lathe, because if you just really need to size a piece of metal, a lot of the time, you know, you need to do one cut to make this thing flat. A Bridgeport is a quicker way to do that than setting up on a CNC machine a lot of the time.
and I think because like industry has really moved towards a machine shop is going to be a whole room full of CNC machines that are like big enough to walk into. A Bridgeport now is cheaper to get, and so like it's very much a thing that is not unreasonable that you could, if you really wanted to do it, you could probably get a Bridgeport for your home garage for a few $1,000s. Getting a CNC machine of like equivalent capacity is not going to happen for somebody's garage that can go through metal. So those are the sort of the dynamics. If you have access to a CNC, the CNC is probably safer because you don't need to be standing right there, like right out next to it, and you get more detail. But like Adam was saying, the Bridgeport is often faster for like, I just need to make this flat and like just go across the top one time. It can usually be faster.
And especially living in Connecticut, you should be able to find a used Bridgeport if you're really looking for one.
I
Yeah.
believe we have one for sale.
Is the
Yeah, we do actually. Yeah, we have three.
being
Third one is, yeah.
uh,
So if you wanted to get one, you can
I know a guy.
leave. It's Leor.
It is Leor, yeah.
That's the guy.
Oh.
Yeah. No, please.
Would you want to switch out the drill for like different materials like steel versus wood?
That's a great question. Yeah, we have in here, we have 3 active CNC machines. There's 2 in the wood shop, the Shipoko and the Gerber, and those are for wood. And then we have another one. Oh, the embroidery CNC. That's true. But it's sort of a different.
I know it's a different.
It's a different beast. That's fine. So 2 in the wood shop, the Shipoko and the Gerber, and then the metal Tormach one is really more for metal.
Both metal one?
Acrylic you can cut on the wood one. The metal one, like the capacity of the Tormach is 8 inches. It's not big. And it's meant for small metal pieces. There's a brazing iron with the MakeHaven logo that we'll show you right after class. But it's good for, I have a small part and I really want a nice detailed thing, and it can totally do that out of metal. If you want to do plastics or wood, that's more in the wood shop. The tools are often the same, like the actual cutters themselves, but the control and sort of how you interact with it can be pretty different. But in terms of like how difficult is the machine to actually use, they're all about the same. Once you learn CNC, they're all pretty similar.
the computer. I
Yeah.
just one last thing that we kind of glazed over, but
Sure.
end mill is the kind of cutter that you use on Bridgeport.
Oh yeah. Cover that in our CNC week, but yes, let's talk about it.
Okay, well, I just, for the sake of an end mill and a drill bit look more or less the same. Flutes going around, but end mill has square corners at the bottom, and it's actually sharp on the sides.
Right.
So the flutes have sharp cutting edges, so when it moves sideways through material, it'll be cutting and it'll leave a nice flat bottom, versus a drill bit only has edges at the bottom, and the flutes are just for carrying chips up out of the hole that you're making.
Right.
So end mill is the milling tool of choice.
That plays out in their price difference also. Like if you, I don't know if you've ever laid a floor, but you might break a few drill bits into your floor. If you're drilling a whole bunch of holes to attach it to joists, maybe by example, never done that. The drill bit though is meant to be consumable, and they break. They're both consumables, in the process of using the tools, the drill bit or an end mill. But a drill bit is going to cost you $1 to have and break. An end mill could range, but $1 is like probably too cheap for the end mill. End mills, the cheapest I'm willing to buy them on Amazon is like a 5-pack for $25. So it's $5 a pop. But when I want to get a nice one that I'm going to hold on to and make sure I know exactly where it is all the time, I'm paying like $30 for that one end mill, and that is still a bargain basement end mill. So they can come in a whole range of prices, but like think about the complexity of them. You have to sharpen it along a curve that traces down its body versus a drill bit where you're just sharpening the tip. So which is probably 2 straight lines. So that's all things to consider. Here is actually inside the Tormach. This is, I made this into a block of aluminum, and it is the thing that we'll use to put a wax stamp on your diplomas at the end of this. But this is an aluminum block that it was able to work its way through and cutting out sort of the Made at MakeHaven logo. This is a failed attempt for a few reasons, but one is it's going to be a stamp and I needed the mirror image of that. So I had to do it again, which is fine. There's a lot of detail and trickiness with it, but once you get it, it's not too bad. Here's a Zelda shield that I gave my sister for her 10-year wedding anniversary. She had a Zelda wedding, so it was an appropriate gift. I'll show you later. And then Ruby down here using the Gerber. The Gerber is our large CNC machine. These are all run by G-code, and so they're spiritually very similar. But the Gerber and the Tormach have different sizes, scales, rigidity. There's lots of different things to learn about them. And as a general attitude, if the word code and G-code makes you nervous right now, the good news is you should never in a modern world write your own G-code. Never, just don't. A machinist will want you to know how to do it. If you're going to apply for a machinist job, you should know how to read and write a little bit. But in the modern world, you don't want to learn G-code or how to read it or write it really.
It is a fun fact that our CNC machine downstairs is the brand that G-code is named after.
Oh, Gerber code.
The language that CNC machines speak just kind of happens to be named after the company that was making CNC machines way back in the 50s or whenever they standardized it.
Yeah, no, that's very fun. So there's that. Also, other machines use G-code, but we don't need to talk about it as often, like 3D printers. The laser and Final Cutter use some weird version of G-code that's slightly different, but they all use, it's just commands that move the machine around. So instead of turning those knobs by hand on the Bridgeport, the CNC does it robotically.
It's the water jet also.
The water jet also does it robotically. It uses a slightly different G-code-y thing, but it uses that OMAC software to manage it, so you'll never need to see the code or touch it, which is perfect. In this process, let's say you have a thing that you want to CNC, you are going to do a whole set of things. You're going to have the idea, you might need to 3D model it, then turn that model to toolpaths, which is a process. So designing it is CAD, then there's CAM, then you export it to G-code, then you home the CNC, then you run the CNC, and then you clean up the work area. There's a whole series of steps. But if you ever want to if you ever pay close attention to Chris, he might just have an idea, and then an hour later he has a thing. And you can get very good at that process. It's just a whole set of steps that you have to go through. Like the metal things that we passed around last week, I'm just saying, boy, it'd be really nice if we had example metals. And he's like, oh, I got this little piece of titanium. And then 25 minutes later, he showed up with titanium, the TI engraved into the top of it. Because that's just how he works. So you can get really good at it, but it takes some practice. Water jet cutting. So lots of you already know about the water jet, which is very, very exciting. It's an ultra high pressure water and sand combo. So there's the water and the garnet, and you can cut through just about anything. We've got some cool examples that we're going to look at later today during show and tell. We cut some glass throughout the week. There was some metal that was cut. And then other things that you can cut ceramic tile, you can cut an apple. There's a water jet channel on YouTube where it's literally dedicated to just putting weird things under the water jet and seeing if will it blend videos from long ago.
Oh, yeah, say that.
Yeah, the water jet channel is fun. They did a rubber band ball once. That was fun. That was a good one. A frozen pizza, I think also. But here are examples of things that you may water jet, like a raw stone. So the stone like this, you can totally blast through. It just takes longer. If you're going to do something very tall, it takes a long time. If you want to have a nice inlay in your front entryway, you can do that. If you really want your decor to yell Montana, you can do that. Where you can cut through glass, stone, sheet metal works really well. Plate metal works really well. All of those different things cut really nicely on the water jet. There's essentially not a limit to what the water jet can cut. It's just going to go slower or faster based on the material and how much it rejects it. The other thing is that if you have a very brittle material, it is a lot of forces, so you have to think carefully about where and how it's going to be held. And the water jet has this big tank of water. And as a general rule, I would say try not to put your hand in there. You want to also make sure while you're using the water jet that you don't have to go fishing afterwards. Because one, like the water is kind of gross, and two, who knows what sharp pointy things are down there. And so there's every so often if you scroll through the water jet channel, you'll see strange things Chris finds at the bottom of the water jet when he drains them.
I found a peace sign today.
No, but that was.
Every
Understand.
yeah, probably quarterly the water jet gets fully drained. But most of the time I think it just stays full of water.
For that naval seal, like what would actually cut?
So these are all different marble or tile that were cut. They were all cut on the water jet and they all just sit really, really tight together. And so like each color you're seeing was a different original starting color of a piece of stone, let's say stone, right? So there was some sort of an orange stone that was cut and they were able to do this, then a white stone, a gray stone, a brown kind of stone. And each of those were cut into their geometry. Somebody had to plan out the design.
Department of Navy, that part,
Mhm.
actual letters.
Yeah.
Into the blue.
So it would have been, they would have needed,
First they did the blue and then
it just fits
Cut
that
it
well.
out.
Yeah,
they
they,
cut the blue out and.
yep.
Pieces.
Yeah, it's like a wood inlay,
Mirror the
Yep.
whole way. Okay.
a negative through the whole thing.
You said when you're drawing, it's so hard to do.
Yeah.
Like,
You said it runs on G-Shows, like that's how.
It does, and let me pull up the Omax software that I have installed.
Oh, Max's.
So when you get bad on the water jet, you also learn how to do the G.
Yeah.
Eh,
I didn't like designing and like, I did my design in.
You get started, I would,
did my design in Inkscape, let's not like.
I would say you
and
get
then
started with
exported
it.
Yeah, to the Omax.
Okay, so here's the Omax software, and if we sort of look at this area over here, the design is right here, and then the machine knows that the water jet is going to blast out this pink area, so it does the cut. You have to sort of tell it like this is my waste area and this is my cut area. And so thinking about the Navy SEAL on the floor is that somebody would have had to make that design, probably with a set of vector lines, and then it's on the blue, you'd have different choices about what's waste. Like in here, it's clearly making things that are bizarre, like where it sort of pokes into your design. But anywhere that it pokes in, like those are waste areas of the base metal that this would be cut out in. So there's a lot of choices that go in to inform how this is made. This is sort of the CAM end of your design. The CAD end is if I could turn, I'm not good at this software, to be clear. I can do vector design, but Omax software is still a lot of figuring it out and gnashing of teeth. But the design here, you make choices on which side of that line you want it to be on. Or do you want to cut right on the line? So little micro choices like that really build up the process to doing this. Those little micro choices of manufacture, that's what CAM is, computer aided manufacturing. And that's a process that we'll dive into more. But if you really love the water jet, this will just be a thing that it's worth dealing with, because you can make such cool stuff with it that you want to learn this process. And while I am not super great at it, it's because I haven't done it a lot. If you make 3 or 4 things in the water jet, you'll get good at it in just a few tries.
So Chris, you're saying like, I get it, I know how to turn it on, I know how to use it, I know how to like click in now. But in terms of like formulating my idea and getting it into there and figuring out one cut versus Chris can help
Chris can help with that.
Understand that part.
And
right?
there's tutorials online also, so you can watch videos on how to do it. Making the design, we have sort of looking ahead, and I want to finish what we're doing. But we're gonna have a week where we talk about vectors and the laser cutter. And so as you learn the vector design for the laser cutter downstairs, that'll directly translate into this. So as you get better at the laser and then the vinyl cutter and some other machines, it's really skills that build together. So that's part of why we like doing all this as one big foundations unit. Because all the pink lines are vectors, and the like thin pink lines are vectors, and the rest of it is design stuff.
So is vector just points?
The vectors are just like the shapes. Yeah.
Okay.
Yeah, just the shapes of what you want to have. And then there's choices around what do you want it to really, how are you going to make that shape happen? So there's limits and precision and things to unpack with that. And we have a CNC unit where we really get deep into the weeds with that. But it's fun. There's a lot of fun you can have with the water jet without ever like really bumping up against that. Nobody's first project is going to be that Navy floor thing. But if you want to make this, well, like you'd honestly never bump into it if you made that handrail. Like your design is basically going to work out in the way you want it to work out. You won't have to think about the curve of your cut. Like it'll be very, very easy to do. If you wanted to make this thing, you won't care too much about the details of the curve. Or if you're making a straight cut through a rock, all of those details are gone. You just sell it, go for 12 inches and take a half hour to do it. So it can be pretty simple, but if you wanted to get deep into the weeds, it takes some practice and getting there.
Can you design something on CAD software and export it to the Max?
You sure can. That's a pipeline that we will absolutely be talking about more. There's a lot of software in that stack though, so you've got to really sort of learn the pieces and put them together. But it is possible. Okay, electroplating, electroforming, and chemical etching. We're going to sort of zip through these together. These are fun. I don't think a lot of people do these, but they're really, really cool to see happen. I don't know a lot of people do them here. But basically, it's possible, and this is me maybe more as a chemistry teacher, to take and make thin metal deposits on things. So if you want to coat something in copper, like these adorable little baby shoes, you cover them in something conductive, and then you stick them into a copper bath and do something with the electricity to move the copper from an anode to that conductive cathode. And so this is a process that you can look into, and you can really coat things in lots of ways. If you've ever seen a bucket that looks sort of like this is a galvanized bucket or galvanized nails. That's putting a zinc layer on a steel or an iron nail. The iron is adding all the strength, but it would rust, and then you'd have a problem if your nail rusts through over a long period of time. So you put this galvanized layer, and zinc on the outside surface doesn't rust and doesn't let the moisture in to let the steel underneath rust. So it's a really nice way to make a bucket that's waterproof and strong and light and won't rust over time. So that process can be useful, or if you have parts that you want to cover in a brass coating, or this looks like gold pogo pins for electronics. There's a lot of gold that goes into, if you're buying like high-end cables, which are less popular now than they were back in the 2000s. I remember paying an obscene amount of money for cables for like video game systems because they had gold tips. Gold is one of the most electrically conductive materials out there. And so if you want to sell high-end electronic parts, you can electroplate the surfaces with the very tiniest amount of gold and then say that they're more premium. I'm just gonna, okay, great. All right. Yep. And so electroplating can be a really cool process. If you want to chrome something like this tire down here, that's an electroplating process. So all of these are really neat processes, and they're pretty doable. You just need a voltage source and an anode of the base material you want, a way to make that material come through, and then a medium that has sort of extra ions to place. This is the sort of thing you're probably not going to just imagine how to do it on your own. You're going to look up how to do it and follow those instructions very carefully. But it's a really cool way to add some neat properties to materials by mixing them together.
There's a reverse version of this that gets rid of rust there.
This one right here. Yeah. Yeah. And so if you want to remove the top layer of something, it's usually called etching. And so if you like this suit of armor was etched, And so across, they made the suit of armor, and across the surface, you do like a masking process, and then you etch. And so it can remove different layers of the material, so you can get a really cool look. Or if you've got a bunch of socket wrench sets and you can't for the life of you see what's on the side anymore, you could do one last time of measuring them and then etch on the numbers across the socket set, or put your name on them if you're a YouTuber named Chris Fix.
Make sure to put your channel ID.
Yeah, your channel, make it merch is what you need to do. But you can remove the top layer to get some neat shapes. Here's copper that has been etched, a copper like rod. And when you etch it away, you get to see all sorts of crazy detail. Those are the grains of the copper that you're looking at. And that's sort of what makes this look really neat, is you're seeing sort of a different depth to the metal. So there's a lot of really interesting processes, but they have to do with the intersection of the chemistry of a metal and then some electricity to encourage atoms to move in one direction or the other. And if you really want to get into this, there's some really cool details you can add. But it's for us, it will be just follow the instructions that someone else has laid out. If you're, a metallurgist or a chemist, you may imagine new processes, but follow some instructions. It works great. As long as you follow the instructions right, it'll just work, which is really nice. It's dependable. It's going to go the way it goes, and you don't have to worry about it because atoms are just going to behave the way they're going to behave. So we made it through all of the processes, and we can definitely talk about more, but mainly this week, we want to talk about different sorts of projects that you might want to do, or getting more badges is a perfectly fine way to go. We do have some grab bag ideas that we realized we have from previous years. And if you wanted to try and figure out some more different things, there's sort of groupings for these. There's like super easy metal table legs, or wind chimes from pipes, or copper wind chimes. There's a bunch of different interesting ways. This is also a longer document for other ideas for units that we have and don't have collectively. It's a bit of an old document, but that's the right link for us right now. But if you're interested and want to do things, I would say go for it. But really, I would say try doing some welding if you're still looking for badges to go after and you're a little unsure about what to do. But that's where we're at for the week. The big thing is we'd like you to still continue to get badges, and if you want to work on projects, we can totally help you. I think the show and tell that we're about to do is going to be really neat to see what people have been up to, and it may inspire you to make your own sorts of projects come to life from what's been going on.